If you've ever watched a concrete pour, you'd probably notice that some concrete looks like wet cement and others appears dry. But they're both at the same water to cement ratio. So why does one look so different? And what does it mean for the performance of the concrete? Welcome to my channel. Today we're talking about the unseen science of concrete curing and what you need to know. I'm your host. For this episode, we are joined by guest host who is a structural engineer and the founder of a company. He has extensive experience in forensic engineering related to concrete durability issues. Thanks so much for joining us today. So thanks again for joining me today. I'm here to talk about the science behind concrete curing, which is something that I don't think people really understand very well. I've been involved with many projects where there's been problems with concrete, particularly with regard to cracking. And when you ask the contractor what was the water to cement ratio, they'll always say, oh, it was 0.45 or whatever it is. The typical ratio. But then you look at the concrete and it's clear that that's not the case. It's actually much higher than that. They just didn't understand it. And so it's important to understand the water to cement ratio, but also how that water reacts with the cement and the aggregates to determine the amount of water that S actually needed to make good concrete. Concrete without enough water will be difficult to place and finish properly. Too little water can lead to poor workability, segregation, and insufficient consolidation. On the other hand, too much water reduces strength and durability and increases the potential for cracking. Achieving the right balance between these extremes requires some understanding of concrete science and a whole lot of experience. Let's start by talking about the ingredients of concrete. Concrete is made up of 4 main ingredients: cement, water, aggregates, sand and gravel, and air. In order to make concrete, you mix all these ingredients together, and then once it's placed, a series of chemical reactions take place. The cement reacts with the water to form compounds known as hydration products. These products are responsible for the strength of the concrete. The aggregate provides the bulk of the concrete's S volume, and its porous structure allows water and air to be held within the concrete. Sand fills the voids between the larger aggregates and also improves the concrete's workability. Air is typically considered an impurity in concrete, but actually concrete without air is extremely brittle and is more likely to crack. The air bubbles within the concrete absorb some of the energy from applied loads and also allow for some movement within the concrete as it dries and shrinks. One of the most important properties of concrete is its water to cement ratio, often abbreviated as W2C ratio. The W2C ratio is the ratio of the amount of water to the amount of cement in concrete. This ratio affects many of the properties of hardened concrete, including strength, durability, and appearance. When making concrete, you need to find the minimum amount of water necessary to make the concrete workable. Workability refers to a concrete's consistency or plasticity. Highly workable, concrete flows easily and can be placed in congested areas with tight formwork. Less workable, concrete is stiff and difficult to place. Because concrete is a fluid, when it's first mixed, it needs sufficient water in order to flow into all the nooks and crannies of the forms. If there isn't enough water, the concrete won't fill the forms completely and will be subject to segregation and may not consolidate around the reinforcement. The ideal concrete has just enough water to reach the furthest reaches of the forms and bind all the ingredients together. In general, the lower the water to cement ratio, the stronger the concrete will be. This is because the strength of concrete comes from the interlocking hydration products of the cement. With less water, there will be more cement available to react and produce a denser, stronger matrix. Lower water to cement ratios also generally mean more durable concrete. With less water, there is less space for harmful ions to penetrate. Chloride ions, for example, can cause corrosion of the reinforcing steel, leading to reduced durability. Low water to cement ratios result in less permeable concrete, which means fewer pores and less surface area for water and other liquids to soak into. Liquid water is one of the main causes of reduced durability in concrete. Water can enter through the pores and freeze, expand, and eventually break apart the hydration products and the aggregates. When this happens, we call it scaling. Concrete that is exposed to freeze-thaw cycles, desing salts, and other elements will eventually fail. Scaling often leads to the rough, pitted appearance seen in many concrete structures. Another way that low water to cement ratios improve durability is by reducing the amount of internal and connected porosity. Internal porosity refers to the number of pores within the concrete. Connected porosity describes the pore structure and whether the pores are large enough to allow water to travel through the concrete. Both parameters must be considered. A highly porous concrete with small pores is less susceptible to water penetration than a less porous concrete with large interconnected pores. This is why it is common to see highly porous but dense-looking concrete in areas like the Hoover Dam that have minimal cracking, while some of the newer concrete that doesn't look all that porous has extensive cracking. A low water-to-cement ratio results in a denser, more compact concrete with fewer pores and less interconnected porosity. In addition to improving strength and durability, low water-to-cement ratios also produce a more impermeable concrete that is less likely to show efflorescence. Occurs when water carrying salts and other minerals evaporates from the concrete surface, leaving behind a white powdery deposit. While it's not structurally significant, efflorescence can be an eyesore, an indication of a lack of quality control. It is important to note that achieving a low water-to-cement ratio is enough to ensure a strong and durable concrete. The concrete must also be properly mixed, placed, and cured. Improper placement or curing can reduce the density of the concrete and increase the water-to-cement ratio, even if the mix design called for a low water-to-cement ratio. Also, factors such as temperature and humidity affect the rate of hydration and the amount of water required for proper workability. So how do we know what water-to-cement ratio to use? Typically, concrete is designed for strength and durability requirements based on exposure conditions. For example, the exposure condition for the Hoover Dam was such that the concrete only needed to be resistant to water that would leak through the structure, rather than being exposed to high-velocity water or fluctuating water levels. Based on this exposure condition, a water-to-cement ratio of 0.45 was specified. For this concrete to perform properly, it had to be consolidated very well. Consolidation is the process of removing air bubbles from concrete to achieve maximum density. Without proper consolidation, air bubbles remain trapped in the concrete, which reduces its strength and durability. Even with low water-to-cement ratios, air bubbles can remain trapped in concrete, reducing its properties. The concrete mix used at the Hoover Dam was very stiff, which made consolidation very challenging. Concrete with a low water-to-cement ratio tends to be stiffer, which makes it more difficult to consolidate. To address this, special equipment such as vibrating heads and internal vibrators were used to consolidate the concrete. Proper consolidation was critical to the success of the project. Ultimately, the combination of a low water-to-cement ratio and proper consolidation led to the creation of a strong and durable concrete that has stood the test of time. Today, concrete is often mixed at a central plant where the ingredients are batched and mixed in a central location before being transported to the job site. This allows for more consistent concrete. Still, challenges remain in terms of placing and consolidating concrete, especially in congested areas or when there are difficulties with the forms. Placing concrete in congested areas can be challenging due to the difficulty in reaching all parts of the forms. This can lead to segregation of the aggregates, which can reduce the concrete's strength and durability. In congested areas, concrete should be placed in layers, and each layer should be consolidated thoroughly to ensure proper mixing. This can be done manually, or with the help of mechanical equipment such as vibrators. Forms can also present challenges for concrete placement and consolidation. If the forms are not rigid enough, they can move or shift during placement, leading to uneven concrete surfaces or incomplete filling of the forms. In these cases, the forms should be secured properly and concrete should be placed and consolidated carefully to prevent any movement or settlement. Advanced techniques such as using pumps to place concrete have been employed in situations where traditional methods are not feasible. Overall, modern construction techniques and quality control measures have helped to mitigate many of the challenges associated with concrete placement and consolidation. Thanks for joining us today, everyone. I hope you learned something about the unseen science of concrete curing. And please subscribe to our channel for more videos like this in the future. We love teaching people about the engineering marvels around them, and it's a lot easier to do that with your support. So please, hit the like button. Subscribe and comment below with any thoughts you have on the video or suggestions for topics that we should cover in the future. We love interacting with all of you guys and hearing what your thoughts are. So, thanks again for joining us today. We'll see you next time!